report again from Maria. All right, so we took a look at the homework. Nobody had any questions they wanted to ask at this time. Played with activity 1-1. Now it's time for section 1-2, playing with patterns. And let's hope my whiteboard works. Come on, there we go. All right, so section 1-2, patterns. So the patterns that we're going to look at are numerical and geometrical. And I'm just going to start off with some simple patterns and see if you can help me extend them. So the first pattern is 1, 2, 3. Does anybody, actually, if you could, on your paper, write down what you think the next 3 terms are in this pattern? And a term in math is just another word for number. What are the next 3 numbers in this pattern? Write down what you think they are. And my hope is that you wrote 4, 5, and 6. Some patterns have a name. These are called the counting numbers. Sometimes they're also referred to as the natural numbers. And when we count out a pattern like this, there is always a first term, and a second term, and a third term, and a fourth term, and so on. All right, let's do another one. How about 2, 4, 6? What do you think the next 3 terms are? And then if anybody wants to voice or chat what they think the next 3 terms are, please do so.
8, 10, 12.
8, 10, 12, yeah. So 8, 10, and 12. And this sequence has a name, and you'll hear me use list or sequence. So a sequence is just a list of numbers, the order matters. So again, in this case here, there is a first term, that's 2, and a second term, that's 4, and a third term, that's 6, and so on. And these could be referred to as the even numbers. And sometimes sequences have names and sometimes they don't. All right, try another one. How about 1, 3, 5? What could be next? Anyone like to voice it?
Oh, 7, 9, 11.
7, 9, 11. Nice. Thank you, Amy, also. 7, and then 9, and 11. And what could we call these? These guys have a name? Odd numbers. Yeah, again, sometimes we can name things, sometimes we can't. Odd numbers. How would I tell somebody how to get the next number? So somebody's like, I kind of see it, but I'm not quite sure how to get the next number. What would I tell them to do to get the next number?
Count up 2.
Count up 2. Yeah, that's one way to do it. I might say, is there another way I could phrase it?
Skip count.
Count up 2, skip count. What was the other thing I heard? Okay. Yeah, so add 2, I could say that, just add 2 to get the next number. A few different ways they can go. Okay, let's try another one. How about, let's start with 4 this time. What do you think the next few numbers are? So first, write something down on your paper to what you think they are. And this time I want you to also have a justification for it, okay? So write down what you think the numbers are and then make a little note as to why those ought to be the next 3 numbers.
$13, $16, $19.
Okay, so does anybody else think 13, 16, and 19 here?
Yes.
Okay, So the next thing is, did you write down on your paper why it ought to be 13, 16, and 19? So I'm just gonna, I'd like to have you just pause for a minute and think about that. I need some kind of justification for it.
We are increasing by 3 each time.
Yeah, skip count by 3, count up by 3s, and add 3 each time. And so sometimes when I'm looking at a sequence like this, I might make a little note underneath like, oh, from 4 to 7, that's plus 3. From 7 to 10, that's plus 3. From 10 to 13 is a plus 3. I just keep adding 3 to get the next term. Okay. Are there other lists of numbers we could make that are different from this one by adding 3 over and over again? If so, can you give me an example of a list of numbers where we're adding 3, but it's not this list?
Like 0, 3, 6, 9.
That's awesome, yeah. So another sequence we could have, and I'm kind of running out of room here. I'm gonna squeeze it at the bottom. Let's use blue 0, 3, 6, 9. Yeah, this sequence of numbers has the same pattern, but it's not the same list of numbers. Okay, so I saw that with the even numbers. With the even numbers, they were jumping by 2. The odd numbers also jump by 2, but they're not the same list. So just something to note, just because we can describe a pattern by saying jump by 3 doesn't mean we've nailed that pattern. So what else would I need to tell somebody about this pattern besides you always add 3?
The starting numbers.
Yeah, well, where to start, right? Like this green one starts at 4, this one starts at 0. So if somebody says, hey, can you give me a formula for this green list right here? I could say, yeah, here's the formula. Start at 4, then add 3 to get the next number. And keep adding 3 to continue. So I can describe this formula without an equation by just saying, hey, just add 3. Start at 4 and keep adding 3 repeatedly. There's lots of ways to word that. So all of these sequences had something in common. And can anyone tell me what you think's common to these 1, 2, 3, 4, 5 lists of numbers?
They're all going up.
They're all going up. Yep. Something else?
Adding, all of them are adding.
We're adding, yeah, to make these happen. And that's a special kind of sequences. Sequences where you have repeated addition. Let's go to a new page. Come on. There you go. So pattern sequences involving repeated addition. Are either called, there's a couple different names. Sometimes they're called linear. You might recall that from a previous life in math. Or now normally we'd pronounce that arithmetic, but it's as an adjective, it's arithmetic. So those are all called arithmetic sequences because they involve repeated addition to move through the sequence. So you'll see both of those words that describe them. Linear, we think about linear, I think about the idea of a slope. And arithmetic is that repeated addition, which is like a slope. All right, so I'm going to put up another pattern. We'll come back to that in a little bit. How about more patterns? 2, 4, 8. What could the next 3 numbers be? First, write something on your paper and think about a justification for it. What is the fourth number in this sequence? Anyone?
10.
Oh,
We got 10, we got 12, we got
I got 16.
16.
16.
16. Yeah, I'm going to go with 16. And here's how I'm going to justify it. To get from 8 to 16, I could say multiply by 2. And that same thing works from 4 to 8. And that same thing works from 2 to 4. So here, I have a repeated multiplication. All right, let's try another one. Okay, so if 16 is there, what would be next, by the way?
32.
32 and
64.
64, nice, good. Okay, let's try a new one. How about 2, 6, 18? So I'd like you to write down what you think the next 3 terms might be and think about how you might justify that. To explain to somebody else and they would go, oh, right, I see it now. Okay, anybody think they know the fourth number here?
54.
I believe it's 54 also, unless I multiplied in my head wrong. And then I might need a calculator for the next one. What's the justification for a 54 there?
Multiply by 3.
Yeah.
Times 3 times.
Yeah, so from 2 to 6 is a times 3, and it turns out that fits the pattern here, a times 3, and might as well just keep multiplying by 3. And so if I multiply by 3 again, that would give me what, 150 plus 12, 164?
62.
62.
Yeah, 162. Oops, yeah, thank you. And then let's see, multiplying again is going to give me a 6, an 8, and a 4. 486? All right. So we could keep doing that. Calculator is certainly helpful. And again, we have that same idea of repeated multiplication. Sequences that involve repeated multiplication like this have 1 or 2 names. They're often called exponential. Another name that's given to them is geometric.
Do those mean the same things, exponential and geometric?
Yeah. Yeah, so just like linear and arithmetic mean the same thing, exponential and geometric mean the same thing. Okay, and we're going to come back and play with these some more, but I'm going to come up with some more patterns to play with. And this time I'm going to put a few up here, and I'm going to let you just kind of play around. Okay, so let's call this pattern A. All right, pattern B. And pattern C. Okay, so your task right now is to play around and see if you can come up with a few terms to continue and a reason why. So keep them to yourself for the moment until I ask for them. If you'd like, I don't know if you guys noticed this, you can do private chats to other people in the class. So if you worked with somebody in the class recently and you'd like to chat an idea to them, feel free to do that. but hold off on a chat to the whole group for the moment. And if you're feeling brave today, I'm still going to give a couple more minutes. If you're feeling brave today and you'd like to try and explain to the group one of these, A, B, or C, just put a note in the chat to everyone that says, I'd like to try A, or I'd like to try B, or I'd like to try C. Does anybody think they have the next three terms for A, B, or C that they'd like to volunteer? Let's play together now.
I might think I have A.
Okay, what do you think's next?
15, 21, 28.
15, 21, and 28. And do you have a reason you think that might be the case?
It's kind of hard to explain.
Okay.
So from like 1 to 3, I added 2.
Yeah.
From 3 to 6, I added 3. From 6 to 10, I added 4. And so I just counted
Oh,
up from 10.
nice. That is a beautiful pattern. I love it. Yeah.
I think I have C's.
Yeah. So that is the pattern there. Now, who said that? Sorry.
I said that. No, it's okay.
Okay. Hang on, C, for one sec. On A, we've seen this pattern before. Does anybody remember where we saw that pattern of numbers? No takers at the moment? Okay, that's all right. We'll come back to it. All right. So let's see. Avalie, you think you have C. What do you think would come next for C?
13,
And?
21,
And?
34.
Okay. Can you tell us about it?
So it's basically like you're counting backwards from numbers. So like for the 1, you added it by itself, and then the 2 you went and you added 1, and the 2 you added, or the 3 you added 2, the 5 you added 3, and the 8 you added 5. Does it like make sense how I'm explaining it?
Yes. So
Okay.
here's another way to look at it. If I take 1 plus 2, that gives me 3. If I take 2 plus 3, that gives me 5. If I take 3 and 5, that gives me 8. If I take 5 and 8, what does that give me? 13. Okay, so we're gonna have to think about how we would describe that besides drawing a picture, but drawing pictures are great. That's one way to definitely solve a problem. All right, does anyone have any luck on B? Cool, all right, so I'm gonna try something. When I don't know what to do, I try something that's worked before. So I'm just gonna shift this up a little bit. So in the past, this addition trick we've been doing has worked pretty well. So let's see, 1 plus 7 is 8. And then 8 plus, what, 19 is 27, is that right? And then 27 plus, let's see, what would that be? 37 would be 64. Let's remove that plus for a second. Is there a pattern to the numbers 7, 19, 37? Well, let's see. 7 to 19 is how far? 12. 19 to 37 is how far? 18? Is that right? Okay, I'm going to throw a hint in here. The next number is 125. Does my pattern here do anything significant? Let's see, 64 to 125 is 36 plus 25, which is what, 61? Is that true? Yeah. And then 37 to 61 is how far? Anybody? 24? Does anybody see any patterns jumping out yet? That might help us get the third number. The second difference here is 6. Yeah, this bottom group here, these are jumping by 6. Here, there to there is 6, there to there is 6. So hey, let's try it. Let's put a 6. 6 plus 24 is going to give me 30. And then, oops, I need the blue still. And then I need to add that 30 to 61, and that's going to give me 91. And then I get to add that 91 to 125. What does that give me? That's going to give me, let's put it in red. Let's see, 1 and 5 is 6. 9 and 2 is 11. Carry the 1. 216. Could we continue this pattern like this? It's a little bit of work, but we could do it.
I'm still not seeing where you're getting the green numbers underneath for your sequence to get 125.
1 plus 7 is 8.
Mm-hmm.
8 plus 19 is 27.
Mm-hmm.
So I'm kind of using what happened up here. To get
Right.
from 1 to 3, we add 2. To get from 3 to 6 is 125.
Right. But when you went from,
where did I get the 125 from?
right, how did you know to go up by 61?
I gave you that as a hint.
Okay.
Yeah. And if 125 is correct, the hint I gave, then 216 ought to be correct if this add 6 is correct down here. Now, I'm going to do something else. Remember before I said there's a first term, a second term, and a third term? Just going to make a note of that here. Let's do that in green, say. This is the first term. This is the second term. This is the third term. This is the fourth term. This is the fifth term. This is the sixth term. What could the seventh term be? And sometimes I find it helps to write that that's number 1, that's number 2, that's number 3, to write the 3, to write the 4, to write the 5, to write the 6. Because sometimes there's a connection between the answer and its position. So question, is there a relationship between 3 and 27, between 4 and 64, and between 5 and 125 that's the same relationship as I move across?
They're all squares?
Almost. Ooh, you're getting hot. Not squares,
That's square.
because like 3 squared is 9.
Okay, right.
Would it be
Exponents.
cubed?
That's what I'm thinking of.
What is it?
Cubed?
Cubed, yes, correct.
Ah,
Yeah, so this is 1 to the 3rd power is 1, 2 to the 3rd power is 8, 3 to the 3rd power is 27, 4 to the 3rd power is 64, 5 to the 3rd power is 125, 6 to the 3rd power is 216, 7 to the 3rd power, I have no idea what that is. I'm going to whip out a calculator. 7 raised to the 3rd power is 343. Let's see if it fits the other pattern. Okay, so I think, according to my calculator, 7 to the 3rd power is 343. To get from 216 to 343, let's use a calculator for that too. 343 minus 216 is 127. So that's that green difference. 91 to 127 is how far? Anybody?
36.
36. Does that fit the 6 pattern at the bottom?
Mhm.
Yep, it fits that pattern. Okay, so A and B have something in common that's not obvious. C is a whole nother animal. We'll get to that one in a minute. It turns out we could write a formula for this one right here. Usually the position of the number is called n. So if n is 4, the answer is 64. If n equals 5, the answer is 125. So the formula is n, whatever position I'm at, to the 3rd power. Okay. Now, did anyone recognize the pattern 1, 3, 6, 10, 15 yet? Did that ring a bell? It's in your notes. We talked about it a week ago today.
Well, when we did the handshakes, we had a
Yes,
pattern.
that's the handshake problem. And we found a formula for the handshake problem. Now, these are handshakes, not introductions. That was slightly different. Okay. I'm gonna get to that in just a second. I'm just gonna show this another way, and then we'll come up with a formula for it. I'm gonna draw a picture of it. Okay, this is that same pattern, but in a picture. There's 1 circle here, there's 3 circles there, there are 6 circles here, and there are 10 circles there. How would you tell somebody how to draw the next picture? What would we tell them to do?
Add 5 circles to the bottom.
And then continue up 4, 3, 2, 1, or just add 5 to the bottom of the previous picture. Yeah, so we'd get this picture with the one before it stacked on top of it. And that would be 15 right there. Okay. Now, interesting thing to note about this, just a slightly different way of looking at it. This is the first term, and that's the second one, and that's the third, and that's the fourth, and that's the fifth. What I want to do is I want to make a connection from the number 2 in the second position to the answer 3, from the third number to the answer 6, to the fourth position in the answer is 10. So I'm going to try to make a connection to that. So for the 6th one, which is about to come, what I need to do is start with 6 at the bottom and then add 5 above it, and then add 4 above that, and 3 above that, and 2 above that, and 1 above that, and whatever that sum is the answer, Agreed? Anyone not with me there? I'm gonna take that as a yes. So I just have to add up 6 plus 5 plus 4 plus 3 plus 2 plus 1, and that's gonna be the answer. If somebody said, okay, well, what's the 100th one, smarty pants? Okay, so to get the 100th one, I would have to put 100 at the bottom, and then what would be above that?
99.
99, and uh-oh, I don't really want to do this. 98, oh my gosh, this is going to take a while. All the way down to 2 plus 1, right? That's a lot. Now I could start from the top and count down, couldn't I? I could start with 1 at the top and then add 2 and then add 3 and then keep going. And at the end, I would have to add the 99 and the 100. Okay. But check this out. This is kind of cool. So I could do it either way. But if I stack these two, what do you notice about the vertical alignment of this list when I reverse it and line it up with itself? What happens there?
It's all 101.
Yeah, every time I get 101. Oh my gosh, how many 101s are there?
All of them.
How many?
Five.
Nope.
Oh, excuse me. Everything in between.
Yep. How many altogether?
100?
100. Yeah, there's 100 numbers here, 1 through 100. So in this, I've just made 100 101s. Now, that's kind of like the handshake, right? If there were 100 people in the room, they would each have 100 people to meet. So as far as introductions go, the answer would be 101 times 100. But these aren't introductions, they're handshakes, or they're just dots in a picture. I doubled the row here, so I have to divide that by 2. So let's check that up here. 6 plus 1, right? Basically the first plus the last would be 7. Multiply that by 6, divide by 2. So 2 goes into 6, 3 times 7 is 21. Is 21 the correct number of circles that should be in the 6th figure? It is, isn't it? So then the 100th figure here should have 100 times 101 over 2. 2 goes into 150 times. I think 50 times 101 is 5,050. There would be 5,050 circles in the 100th figure here. How would I generalize this for n with a formula? So in this case up here, n was equal to 6, and then I took 6 times 7 and divided by 2. In this case right here, n is 100, and I took 100 times 101, and then divided by 2. So what's my formula going to have in it, for sure?
2. Divided by 2.
What's that?
Divided by 2.
They're going to be sure there's going to be a divide by 2. Yeah, what's going to go in the numerator if I'm looking at, so n could be 2, or it could be 3, or it could be 4, it could be 5. I don't know what it is, so I can only call it n. So n is 100, start with 100. N is 6, have a 6 in there. So for sure, I think there's going to be an n times something. How would I describe the other number if the first number is called n? So this is my n right here. How would I describe that number? Here's my n right here. How would I describe that number? Almost, Emma. Emma wrote n minus 1. Other way. The other number is actually bigger than n. So it should be
n plus 1.
n plus 1 is the other number. Now I put parentheses here. The question is, are the parentheses necessary? Is n times parentheses n plus 1 the same as n times n plus 1 without parentheses? Are these going to be the same or not? No, says Emma, they are not the same. That is correct. Parentheses definitely matter. And I could test it with a number, or I can just kind of reason through it. So if I tried to test it with a number, like suppose we plugged in 3, in this formula here, I have to find 3 and I have to find 3 plus 1, then I can multiply and then divide by 2. So 3 times 3 plus 1, that would be 3 times 4 over 2. That would be 12 over 2, or 6, right? That is the correct answer. If I tried this version of the formula without the parentheses, I would have 3 times 3 plus 1 over 2. Order of operations says multiply first. That would be 9 plus 1 over 2, which is 10 over 2, which is 5, which is not the correct answer. Okay, so the parentheses definitely matter here. I'm going to go back a screen for a second to show you a pattern that's kind of interesting. So the formula for this pattern A up here, switch to green, can be written one of two ways. It could be written n times n plus 1 over 2. But some of you took math classes where you were like distributing stuff and factoring stuff. So another way I could write this formula is by distributing this n through, which is going to give me an n squared plus n, and then divided by 2. Okay, now the point of this is, notice that when these red numbers I wrote under the green ones here, get my laser pointer, these red numbers underneath the green ones here, those are called the first differences, right? What's the difference between 3 and 1? It is 2. The difference between 3 and 6, that is 3, okay? If I took second differences here, what's the difference between 2 and 3?
1.
Yeah, it's 1, and the difference between 3 and 4 is 1. The difference between 4 and 5 is 1. It turns out if the formula is going to have a second power as the highest power, then the second set of differences will be a fixed number. If the highest power is a 3, then it turns out you have to do 1, 2, 3 differences before it starts to be steady, right? 6, 6, 6, 6, 6, 6, 6 for this one because of the third power. So if you have to take 3 differences, it's going to have a cube in the formula. If you have to take 2 differences before it's the same number, it's going to have a square in it. If it's the same number with only 1 difference, then that means your formula is the first power of n. So let's take a look at an example like that. And how are we doing on time? Pretty good. So new page. I'm going to go back to an example we had in the beginning, and that's 1, 3, 5, 7. What's next here?
Oh, the 9, 10, 11, right?
Yeah, almost. 9, 11.
11, 13, my bad.
13, yeah. So these were the odd numbers. And these numbers have a first difference of 2, right? To get from one to the other, or you could say they're each 2 apart. A couple ways you can phrase it. It's always 2. The first difference is constant here. So I'm just going to make a note. First difference is constant. That means this is what we call that's supposed to be an arrow, by the way, not a very good arrow. That means this is what we call a linear, there we go. Sequence. Does anybody remember the other name I gave to a sequence like this?
Arithmetic.
Arithmetic or arithmetic, yeah, I can say it either way. So it's a linear sequence, or you could call it arithmetic, either way. So because the first difference is constant, that means the formula, sometimes called the nth formula, is going to have an n to the first power in it, which I'm just going to call n. Because that difference is 2, it has to be a 2n. Okay? So that first difference is the multiple of n. Because this is repeated addition. Repeated addition is multiplication. Now, sometimes that is the formula, but often you have to add or subtract some number to adjust, to shift side to side. Can you tell here if I have to add or subtract a number to get the right answer? Anybody want to take a guess? So these numbers in blue at the top, those are what I'm calling n. If n is equal to 3, what's 2 times 3? 6. What do I want it to be? I want it to be 5, so what should I do to tweak the formula?
-1.
-1, yeah. So usually what happens is I do something like this. I see that the first difference is always the same, so I say, okay, my formula's got to have a 2n in it. So then I check it. And the book shows a slightly different approach than this once you read section 1, 2. So I say, okay, let's let n equal 3. Then the formula says take 2 times 3. That is 6. I want it to be 5, so I say, oh, okay, subtract 1 to make that happen. And that gives me the 5. So then I check again. So now I think it's -1. So then I check for a different number, like maybe n equals 4. When I check it, 2 times 4 minus 1 is 8 minus 1, which is 7. And yeah, 7 is the right value. Okay. So because the difference is constant, we have a repeated addition involved. So the formula has to be 2 times the term number. Then the question is, do I have to adjust it a little bit? So let's do another one of these. Let's see, way back in the beginning, I had, let's do this one, 4, 7, 10. Okay, so the pattern this time is 4, 7, 10, and I'm just going to write a couple more, 13 and 16. And the pattern we noticed is that this is going up by 3 each time. This is the first term, that's the second, that's the third, that's the fourth, this is the fifth. These blue numbers are the numbers I'm calling n. So now what I want is a formula where I can just plug in the number n and out pops the answer. Because if I want the 100th term, I got to add a ton of 3's starting at 4 to get there. And that's going to take a while. So what I'd like you to do is take a guess at the formula, check your guess, modify it, see if you can come up with the actual formula. So don't post yet, just give everybody a minute to think about this for a moment. Excuse me. Okay, so does anybody want to take a shot at a formula here?
3 times n plus 1.
Okay, I got a couple people that seem to agree with that. So we think the formula is 3 times n plus 1. And just to justify how that's the case, once we see the first difference is constant, then that means for a formula, we have to have 3n in it. Then the question is, do we have to add or subtract something to tweak it? So for example, for the first term, 3 times 1 is 3. I want it to be 4, so maybe I should add 1. Check. Let's say n equals 4. 3 times n equals 4 plus 1 is 12 plus 1, or 13, which is the right number. So that does check. So yep, that is the correct formula there. Cool, we're making progress. Is this type of pattern linear or geometric or something else? Linear, geometric, or something else? Anybody? Linear, that is correct. So, or I could say it's arithmetic would be another way to look at it. So I'm going to call it linear. Just to double check the linear nature of it, if I call the blue numbers like x's and the green numbers y's, and I went to graph them, they should line up. So let's see, the y's, we'll just go by 2, 4, 6, 8, 10. I'm not going to do all of them. 12, and then 1, 2, 3, 4. That should be far enough. So these are my x's, these are my y's. The x is the end, the y is the result. And if I plot the points, 1, 4 is right there. 2, 7 is right there. 3 goes with 10, and 4 goes with 13. Can you see the points line up here? Nice straight line. And just a reminder of how this relates to math you've done before. When things line up like that, it's related to y equals mx plus b. We've seen that formula before, where m is the slope. And I can see here that there's a rise of 3 and a run of 1. So the slope is 3 over 1, or 3. To get the y-intercept, I would just trace this pattern backwards. So that would mean go down 3 over 1. And so that right there should be the y-intercept. And so that's that 1. So you've actually done stuff like this before. I'm just presenting it. It's being presented in a different way. Looking at counting patterns instead of graphical patterns, but it's all related. Questions on that relationship between like a line and this arithmetic pattern?
What would you use exponential patterns for if it's not for graphing?
Yeah, good question. So exponential patterns come up in a variety of places. Oops, wrong button. Need a new page. If you have a credit card, then you have to pay interest. And it turns out the way interest works, if you don't pay everything off, then there's compound interest involved. And compound interest is where the exponent changes. So for example, just a simple one, if I, let's see, if I had $100 that I owed, and let's say my monthly interest rate was 2%. That would be a 24% annual rate, which kind of sucks, but some people have that. That means that if I don't pay this off, every month I owe on top of the 100 an extra 2%. So that means every month I actually owe 102% as a decimal. And as the months go by, that accumulates with a power. So if I don't pay off the $100 at 2% per month, this would be the value that I owe after n months. Inflation rates tend to be exponential or geometric patterns. Populations kind of grow exponentially. Bacteria growth starts exponential until, you know, there's a kind of a wall of resources the bacteria hit. There's probably a bunch of other examples I'm not thinking of off the top of my head. So sometimes things change by a fixed amount. Sometimes things change by a fixed percent. If they change by a fixed percent, then that's an exponential growth pattern. Like maybe you work for a company and they say they'll give you a 2% raise per year and they'll start you at $100,000. Then this would be your salary in thousands over the next 10 years, if n was 10 for years. As opposed to getting a fixed raise, like $100 a year, that would be linear or arithmetic. Good question. All right, let's go back to another pattern we saw. Let's take a look at that 1, 2, 3, 5, 8 pattern. And again, just think about that. This is one I think most of us struggled with. I'm going to put in words how I think this works. To get a value add the two previous values. Okay, so if I want this value right here, I just look back and say, okay, what's 8 plus 5? Oh, well, that's 13. If I want the next number, I'd say, okay, what's 13 plus 8? That would be 21. Does that seem reasonable statement here? To get a value, add the two previous values?
Yeah.
Okay. Now, if we think back to the linear ones, let's go way, way, way back. Oops, too far. Right here. We discovered that there's many patterns that are 3 apart, but you get a different list of numbers. So this green pattern over here, they're each 3 apart, but it's 4, 7, 10. This list of numbers down here, they're each 3 apart, but it's 0, 3, 6, 9, right? Not the same list as above. So to cement which one I mean, this one or that one, I would have to tell somebody where to start, right? Keep adding 3, but start at 0. That would be the blue one. Keep adding 3, but start at 4. So for this pattern over here, I would have to say where to start. So to be more specific here, I would have to say starting at 1 and 2. You could start with any 2 numbers you want. Like I could have started, we could have done a totally different one. I could have started with 3 and 4, and then the next number would be 7, and then the next one would be 11, and the next number would be, what, 18, and so on. So this would be the same starting, right? Add the same rule, add the 2 previous values, but this time it would start at 3 and 4. So because I'm adding the 2 previous values, I need 2 starting points in order to make it work. This turns out to be a very famous sequence. Does anyone think they know the name of this sequence of numbers? It starts with an F. And usually there's an extra 1 in the beginning. Fibonacci, Jimmy, thank you. You nailed it. Yeah, this is called the Fibonacci sequence. Fibonacci. And it's very famous mathematically. It's got a lot of weird properties. My other sequences, I could write a formula. So if somebody said, hey, what's the 8th term? I just plug in 8 and out pops the number. Not so easy here, but I could whip this out on a spreadsheet. So the next class, what I'm going to do is I'm going to revisit all of these patterns, but show you how to do them on a spreadsheet. Okay. I think this is a good stopping time. It's 4:30 now. We have another 8 official minutes. But the spreadsheet stuff, I think 8 minutes is not enough time to get that started. So we've covered more than half of section 1, 2. You have some tidying up work to do in section 1, in particular, writing up your answer to the activity about the peg jumping for 4 pegs versus 4 pegs. And you got a reading assignment to get done soon for section